I think we got cut off in the middle of the last problem when I used the calculator function. I'm going to turn this a little, see if that works better as far as staying out of the way. Okay. Now, our problem is we have a 0.5 kilometer length of high tension power line carrying 25,000 amps of current due east towards New York. And the question is, what force does the Earth's magnet... We know that there's going to be a magnetic field around that current carrying line. What's the force that the Earth's magnetic field exerts on the wire? So first thing we're going to do is we're going to sketch this. And let's make this east, north, south, and west. So our current carrying wire is going to be like this, stretching across the landscape. And the current will be going in this direction. And the Earth's magnetic field, we know, goes from points toward the North Pole. That's why the compass points that way. So this would be the Earth's magnetic field. And this current carrying wire is immersed in it. And because there's going to be a field circling around the wire like that, it's going to experience a force. And let's see what the direction of that force is. So if we point our fingers in the direction of the current, that the current's going, and we wrap them towards the magnetic field, we find that the force comes out of the surface like that. Using the other method, if we point our fingers in the direction of the field, thumb in the direction of the current, the force comes out of the palm. Both methods tell us that this force is coming in this direction towards you. And because we're looking down on the surface of the Earth like that, that means the force is going to be up toward the sky. And the magnitude of that force is going to equal BIL times the sine of theta. And theta in this case is 90 degrees. So we're going to get the maximum force. And we know that B, the Earth's magnetic field, let's label this here B Earth. So we know what these lines represent. B Earth equals about 5 times 10 to the minus 5th Tesla, or 0.5 Gauss. So the force is going to equal 5 times 10 to the minus 5th Tesla times 25,000 amps times 500 meters times 1, which is the sine of 90 degrees. Now, the Tesla is the name for the unit, but it's actually a more complicated unit, and these end up working out to give us newtons. And when I did the calculation, I found that the force equals 625 newtons in the up direction toward the sky, which means the Earth's magnetic field is actually lifting that cable up and helping carry the weight of it. I mean, that's only about the weight of a person, but by contrast, if the current was going west toward California, the Earth's magnetic field would be pushing down on it. So that's the first example. Now the second problem we're going to look at is something a lot of people asked about yesterday. Your book talked about it, but didn't really explain it that carefully. And that's the question of the direction of the force between two parallel wires. So, to get this, we'll need to organize this. So say we have two parallel wires. Here's one. And here's wire number 2. And they're both carrying their current in the same direction. So the current's going that way, current's going that way. We're going to call this wire A, and that's wire B. Let's keep that wire about the same. Okay, now, we know that around wire A is going to be a magnetic field. And we even know the direction of it. If we put our thumb in the direction of the current and wind around, we find over here it's coming out of the page, which we'll indicate by circles. And over here it's going into the page. And that's magnetic field A. Now the thing is, that magnetic field cannot exert a force on wire A because you can't exert an unbalanced force on yourself. So what's exerting the force on wire B is this field from A. Now B also has a field going into the board over here. We'll represent that by X's. And the field loops around and then comes out here. We'll call that magnetic field B. Now, what's going to exert the force on wire A is not this magnetic field, but this magnetic field. And if we look on the right side of this wire, the field is going in, and that extends all the way out. On this side of the wire, the field is coming out. So when this magnetic field contacts this wire, it's going to be coming out of the page like that. And so in order to find out the direction of the force, we're going to turn our fingers in the direction of the current, wind toward the field, and the field is this coming out. We find the force is in that direction. So this wire is experiencing a force from magnetic field B in that direction. And if we use the other method, if we put our fingers in the direction of the field and our thumb in the direction of the current, the force comes out of the palm and we get the same result. Now, how about wire B? What's exerting the force on wire B is the field produced by wire A. And we can see that on the side of wire A that B is on, that field's going in. So in order to find the force, we put our fingers in the direction of the current, curl our fingers toward the field, and that's the direction of the force. And so we find that two parallel wires with current in the same direction attract each other. And if you do that for one wire going the other direction, you'll find that the forces are this way and that way, and they repel each other. So that's the reason for that. And that's a pretty complicated one because you have to apply both right-hand rule number 1 to find the field and right-hand rule number 3 to find the force. So hope that clears that up. If you have other problems in the skill sheet you have questions about, just let me know in the discussion and I'll send a solution along. Okay, have a great day. We'll talk to you tomorrow.